All right, welcome everyone to our final C Prime talk of the semester. So let's go ahead and get started. Let's skip past it. Oh, wait, sorry. Great. Okay, so if you don't know, C Prime is a student group, the physics department that's devoted to increasing diversity, equity, inclusion, and allyship. And one of the ways that we do that is through this talk series where we have graduate students or other researchers give informal talks about their research and their personal life to all of you. So we'll have times of discussion throughout. If you have questions at any point, feel free to interrupt. And today we are privileged to have Olivia Krohn come and talk to us about space chemistry. So I will let you take it away.
Sweet. Thank you, guys. Like Tyler said, my name is Olivia. I work in kind of an interesting intersection of chemistry, physics, and astronomy. And like you said, if you guys have any questions as we go through the talk, please let me know. Definitely want to here to help answer questions. So what I'm going to be going through today is first I'm going to give you guys a bit of an introduction to me, how I came to be before you guys. I've had kind of an interesting journey finding the area of physics I'm interested in, and I thought that might be helpful to share with you guys. I'm then going to talk a bit more about what I mean in my title when I say laboratory astrophysics. What even does that entail? Why are we interested in doing it? And then I'm going to go a little bit more in depth on how we actually do that and what some of the different physics tools that we use to do that look like. And that's going to help us understand how to get and interpret the data that I'm going to show for a particular chemical reaction that we studied that has relevance to physics and chemistry that happens in the interstellar medium. I'm going to throw out the word interstellar medium out a lot today. In many contexts, you can just substitute that straight for space. We're really interested partially in looking at these reactions that happen in space. So some introduction to me. I started my science physics journey at my hometown undergrad institution, Fresno State. It's a state college in the middle of California. I got a scholarship to go there, so I decided to stay close to home. And it was kind of the start of understanding what I like to do science-wise. I always knew I liked science fair. At one point, I wanted to be a meteorologist. Another point, a rocket scientist, an engineer. I've wanted to be so many things. But at this point, I started taking different lab classes. This is my roommate and I doing our Chem 1A lab. And I was really starting to like the hands-on science. At this point, I started thinking more about physics. And my roommate, Layla, started to get interested in being a doctor, which I think is firm proof that she is smarter than me. My first real research experience was through a research experience for undergraduates or an REU at UCLA. If you guys ever have an opportunity to do an REU, I highly recommend it. It's a good way to get to do research outside of your home institution to see what science is like in other places and get exposed to different types of science as well. For me, I got a project on dark matter direct detection, which did sound very cool, and I really enjoyed the bit I learned. I can talk for about 3 minutes about dark matter before someone finds out I don't actually know that much. But I did also find that this area of physics, this kind of high energy physics that's interested in particles, tends to be very data and analysis heavy, very computer science heavy. And I was learning that I did like coding, but I didn't necessarily want to do it all the time. I had a similar experience through Fresno State to go to the Large Hadron Collider at CERN and work with some statistical modeling for the Higgs boson over the course of a summer. And this was also a very cool experience, kind of get to see some of the international science community, also very computer science heavy. And so starting to get the hint that as I moved towards grad school, I probably wanted to do something a bit different. So I started applying to grad schools. I was super excited when I found out I got in here. No joke, I thought it was UC Boulder for like 6 months. Someone had to correct me. It was pretty embarrassing. But early on, I found an opportunity to work in research, collaboration between Joseph Mickle in the chemistry department and Chuck Rogers in the physics department. They were working on a project called molecular rotors. One of the things I got to do was work in the clean room, which is why I'm wearing this ridiculous outfit. It was pretty fun. And I was starting to kind of figure out that I really enjoyed having hands-on science. During this time, they asked if I could work with some of their collaborators in Berlin to work on some ultra-fast spectroscopy. I thought doing science in Germany sounded really fun, so I said yes. Ultrafast spectroscopy is essentially using really fast pulses of light to investigate different molecules. And so two things I took away from this is I really thought molecules in chemistry was really fascinating. I liked to learn how we could use light to find out structural things that was happening in molecules. And I also learned I did not have the patience to work with lasers all the time, which is kudos to my husband because he works in the CAM group and he does that all the time. And I'm just in awe. Unfortunately, around the time I got back, what was happening was the project I was really interested in was running out of funding. And the other projects that the advisor I was working for had for me were going very, very deep into chemistry, a little deeper than I wanted to go. But around this time, Heather Lewandowski was looking for graduate students, and she works on some conjunction of chemistry and physics and really getting to work with some hands-on experimental methods. And so I took advantage of that opportunity, and I have been really happy with that ever since. So what kind of hands-on physics have I really enjoyed doing? This is the kind of stuff that I work with day to day. We're going to talk a lot about ion trapping, so don't worry, you'll see these pictures again. I've gotten to help build an extension of our experiment from the inside out, so definitely getting to actually poke the physics in a way that you can't do at a particle accelerator. Ton of experience with electronics, frankly, an overwhelming amount. Ultra high vacuum systems have been a key part of our experiment and something I've really enjoyed getting to learn more about. And also this lasers have come back and I have enjoyed working with them as well. So this is just a little bit of a cross section. Every day is kind of different in the lab because kind of the trick with this area of chemical physics and atomic molecular optical physics is getting a bunch of things to all work at the same time. And I've really enjoyed that balance. So what are we talking about when we talk about chemical physics? What exactly is it that we're trying to do with this type of more complicated hands-on experiment? There's two primary motivations for the type of research I'm going to talk about today. The first is more of a fundamental question. It's trying to investigate what are the actual underlying principles when we talk about chemical reactions and chemical bonding. If we go all the way down to the periodic table and quantum mechanics and electrostatic forces, how can we use these principles to actually understand why we get reactions the way we do, why some are fast and some are slow, why certain things like to bond and others don't. Another really interesting motivation for what we do is chemistry that occurs in space, chemistry that occurs in the interstellar medium. And this is a very interesting environment to study chemistry for a couple of different reasons. The first main reason is space is really sparse and it's very cold, right? This is kind of something you hear early on. There's kind of a lot of vast nothingness through most of space. And so this kind of brings up an interesting question, which is why do we have molecules in space at all? If the likelihood that you'll have even two molecules in the same place at the same time is pretty small, and even then they might not necessarily react, what does it take to actually get complicated molecules in space? So that's an interesting question I want you guys to start with. How large do you guys think the most complicated or complex molecules that exist in space are? How many atoms? How big do you think we've found molecules? Go ahead and introduce yourself to your neighbor and discuss this question. We'll take a couple minutes to discuss and then come back. Sweet. So let's go ahead and follow up on that question. So by raise of hands, what molecules do you guys think have been found in space? Yes.
I think like hydrogen-based compounds that they have.
Oh, yeah, absolutely. Yep. They have indeed been found. Cool. Any others? I know this is a really specific question. Any other guesses? Any other molecules you maybe heard of you want to throw out there? Or guesses on how big or how many atoms it gets? Yeah.
I vaguely, from memory, remember those one that contains like 100 something.
Okay.
Atoms, and I would guess it was something organic.
Okay.
And I remember hearing that they were synthesizing something that was really complicated.
Okay.
And they were using the scope to determine the structures, but that's about right.
Mhm.
And apparently it's something that's super complicated to simulate.
Okay. Yeah, so you've got a memory of something really big, organic, hard to synthesize and simulate. Okay. You are describing as an interesting molecule. Did you want to add to that?
Voyager 1.
Yeah. Okay. You got me. Great one. Yeah, as far as the molecules that have been made in space by chemical reactions, the biggest molecule was found about 5 years ago. It's Buckminster fullerene, which maybe you guys have heard about at some point as buckyball. It's 60 carbon atoms in this beautifully symmetric structure. And I wonder if maybe it is something you remember hearing about, because it is indeed very complicated, very hard to synthesize, even in a lab. And so even though the astrochemical community that are trying to answer questions like, how do we get such a big molecule in space? Even though they have seen a lot of different, really complex molecules with multiple atoms, both neutral molecules and ions. The ions are boxed here. There's been a lot of molecules found, but there's still a huge step between all of these atoms, which are really very rarely above 10, to something this complicated. And especially in an area like space, where you very rarely have collisions of even two molecules at the same time, trying to figure out how we bridge the gap to form even these, much less something like this. It's a big problem. And this problem is addressed by a couple different research pursuits in the community. One of them is trying to actually measure the spectroscopy of these molecules. So finding out how they respond and emit light, how they respond to and emit light, so that we can look for them in the interstellar medium, but also trying to find out what kind of reactions occur between all these molecules. Maybe try to look for some ways that we're able to form them and to see what they then form with other molecules. And that is exactly what I work on, is trying to look at how these ions and molecules react with each other to try to understand further how we get the chemicals that exist in space. And there's one important specific class of reactions I want to define a little further before we move on, and that has to do with energy. So not only is space sparse, but it's also very cold, right? So when people think about how chemical reactions occur, you might see a diagram like this, where this is representing energy, and this is a weird thing called reaction coordinate. Essentially, what it is saying is the reaction either has to go from left to right or right to left. So if we're looking at a reaction that goes from left to right, here's what we start with, and here's what we end with. But we need a certain amount of energy to go over a barrier in order to form a new bond and ultimately make our products. But in a region like, or the air, where things have a ton of kinetic energy, or in a test tube where you light a flame, a little bit of energy is not a big deal. But in space where there's so little excess energy, it's so cold, this is actually kind of a problem. So we need to be looking for reactions that have this type of profile, where you have the most amount of energy is what you start with, and the whole procedure can be done without needing additional energy. And a very important class of reactions that usually fulfills this is reactions between ions and molecules. Most of the time, ions will always find a way to rearrange to be happier, and so they tend to be very reactive in regions even as cold as space. So how do we actually look at reactions between ions and molecules? So this is the part of talk where I'm going to talk to you guys about the experimental methods we use to actually study a reaction. So the first thing that I want to ask you guys is, how would you trap ions? So go ahead, reintroduce yourself to your neighbors. How would you guys trap ions in order to look at their chemical reactions? So I'd love to hear your guys' ideas. How would you guys trap ions? I will be upfront, there are many ways to do this, and so you guys will probably come up with great ideas that is not exactly what we're going to do, but I'd love to hear them. Yes?
Well, I use a lot of calibrated electronic and magnetic fields.
Okay.
Typically, I've heard of them using like RF fields.
Uh-huh.
I'm sure there's ways to do it with a variety of electromagnetic waves.
Mm-hmm. Yeah, radio frequency electric fields is what we're going to go into in a moment. Do you have an idea why we would have to do that over maybe static electric fields? I know this is not fair. I'm throwing another question on you. You don't have to answer it, but do you have any ideas?
Well, I think with the static electric field, you also need an oscillating component to keep your particle locked in one place so it doesn't just push to one side or the other. But that's a very hand-wavy explanation, so.
I like it. We'll come back to it. Yeah, did you want to add to that?
I guess, yeah, I think, I mean, I don't know how it works, but I would just assume that because you want it to be automated, because you want it to keep your ions in a row. So if it oscillates outside of it, it would like, it would always default back to the node. It will always push it back to the node.
I think what you're describing is we need something that's inherently stable, where even small perturbations make it move back to one spot versus destabilize it. I love this. You guys are stealing my slide from me, and it's amazing. Any other ideas or things you want to throw out there? I know I also heard an idea with magnetic fields as well. That person wants to share.
Yeah, last semester, I think there was a talk, right, specific about trapping ions so that with the laser and something called quantum tunneling, I think.
Okay.
Something with laser management.
With lasers, maybe a magneto-optical trap.
I think it's penning trap.
Was it a penning trap? Yeah, so penning traps is not what this is, but it is another, other groups in the field use a penning trap, which is using magnetic and electric fields in order to do trapping. We're going to use pure electric fields. Before I move on, anyone else want to add anything? Cool. You guys have had some wonderful ideas. I believe a lot of people went to electric fields pretty naturally, which is great. Ions are electric static forces. I'm sorry. Ions are very inherently susceptible to electric fields. As we kind of all learned pretty early in physics, you know, if you have a negative potential, it exerts an attractive force on a positive charge. Like charges will repel. So maybe a first idea would be to have some sort of symmetric setup where, you know, you have these rods that might all be repulsively pushing it towards the center. And so right in the center, you'd have it nice and trapped. But as we already heard, one of the things that it can be inherently unstable about this is it may be stably trapped in this direction, but over here, if you get just a small perturbation, it'll get destabilized and easily fly out these holes. And that's actually a simplification of an actual mathematical theorem that tells us that we can't have a local minima in free space with electrostatic fields. We'll only have saddle points where it's stably trapped in one direction, but destabilized in another direction. But if we're clever about it, we can use this to our advantage. So we have a configuration like this, where in one direction we have negative potential, the other positive. We'll create just this one type of saddle point, where in one direction we have stability, we have trapping, electric potential energy, much like traditional potential energy. We have a hill in this direction, but the ions can roll down the hill, so to speak, in this direction. However, if we switch it fast enough, we're able to actually bring up a potential barrier as it starts to roll down, although we would momentarily destabilize the other direction. But if we flip back and forth between these fast enough, then before the ion actually gets destabilized and comes out of the trap, we will be able to retrap it by moving this field. And using RF voltages going back and forth between these two, we're able to stably trap ions. I find this video is kind of a nice, just mechanical analog to be able to visualize what's happening. This is, of course, just an actual mechanical saddle point. Like, it physically just fits the shape. And so if you were to take an object like a ball and you were to sit it in the center, what you'd see is it does get sloshed around by all this movement back and forth. You've got the forces pushing it around, but ultimately the ball will stay in the trap if you're rotating it fast enough. So the interesting things to take out of this is it does depend on the frequency, how fast you're rotating it, so it doesn't have a chance to escape. And you do actually get some residual heating from this because you're sloshing it around quite a bit. And this is true with the ions as well. But this is kind of a nice picture of how this actually works with the ions as well. And this is our apparatus. We've got 4 rods here, and they have that exact RF potential where we have opposite potential on the crossed rods, and we have a frequency fast enough to keep those ions trapped. But now we have a bit of a problem. because I told you we're interested in doing chemistry that's really cold, like that of the interstellar medium. But I also told you that the way we trap ions tends to heat them. In fact, leaving it just as it is, often this heating can be hundreds of thousands of Kelvin in temperature, and that is really hot for what we're interested in studying. So we're going to need to cool down the ions. And we're going to do this with Doppler laser cooling. I'm guessing a lot of you have heard of the Doppler effect, but I'm going to give a quick recap just in case. The Doppler effect is usually classically described with sound, where if a source is moving towards you, the tendency of those sound waves to get bunched up makes it appear to be a higher frequency when something's coming towards you and a lower frequency as it's moving away. So like the ambulance coming towards you, it sounds higher as it approaches, lower as it moves away. And this effect carries over to light as well. Light has wavelengths and frequency, and the lower frequencies are associated with a redder color in the visible spectrum and bluer as you get to higher frequency. Now, normally, this is not strong enough that this really impacts our vision. But if you consider that even classical speeds will shift a wavelength by just a little bit, maybe even less than a nanometer, and you consider that a lot of atoms and ions are sensitive even down to those tiny differences, we can start to use this to our advantage. And the way we do that is something like this. As soon as the there we go. Whoop. Spoilers. So this is a graph looking at the likelihood for an ion to absorb or scatter a photon or packet of light. And that really depends strongly on frequency. So if we have a system that's very sensitive to the frequency of light like this, what we can do is shift a laser light slightly to the red of this. And that will have a very different effect on whether or not the atom or ion is moving towards the light or away. Where if it moves towards the light, it's very likely to absorb that light. And if it's moving away, it is much less likely to do so. This is more of a pictorial description of Doppler cooling. The idea then is that it is unlikely to absorb the light if it's not moving at all, or if it's moving in the same direction as the light. But if it's opposing the direction of the light, it's more likely to absorb the light, get into an excited state, and then over time, it will re-emit that photon, that packet of light in a random direction. An analogy that I think kind of helps to think about what is actually happening momentum-wise here is, say you have a friend that's sliding on ice towards you, and you were to throw a basketball at him. As he catches it, that may slow the person down a little bit, and he may then throw the basketball in a random direction. And so if you were to do this over and over, your friend would then slow down in that direction and diffuse that momentum in a random direction. And this is actually pretty powerful to be able to cool down the motion of ions from really fast velocities and get them pretty cold. And the reason we're able to do this has to do with the energy structure of a particular chosen ion. So our trap, we use calcium. This is a quantum mechanical energy structure. If you guys haven't been introduced more to quantum mechanics, don't worry, I'll focus on the important rules that are occurring here. You may also notice S and P orbitals from chemistry. The important thing here is that calcium doesn't want to absorb the amount of energy any less than this full transition. It wants exactly that energy gap. And that energy gap is tied to a very specific wavelength of light. So now we kind of have that frequency response that I showed you in the previous slide. And so this is what allows us to actually redshift light slightly below it and do our Doppler cooling. So this would look something like it absorbs, it gets excited up here. And then the rules of quantum mechanics, so to speak, say that it can only stay here for a short amount of time. And when that time is up, it will spontaneously let go of a photon and come back down either to its original state or this side state over here. The side state over here is a little bit annoying, because the rules for calcium say that this will almost never happen. And it happens so rarely that if it gets stuck over here, then we're effectively not able to use it for cooling anymore. So we do need to use a specific wavelength of light to make sure it doesn't get stuck over here. But with just 2 lasers, we're able to actually get calcium down to millikelvin or microkelvin temperatures, which is pretty powerful. We also have a nice side effect of this, and that's that this spontaneous photon that's given up, it goes in random directions, but some of the random direction is up towards a camera that we just happen to be sitting right above it. And what's pretty amazing about this is it means that we're able to visually look at the calcium that we're cooling as we cool it. Oh, that's right. And this scales all the way up to when we want to have thousands of calcium ions, all the way down to a single ion. And this is very sneaky because normally you would say that you can't see a single atom with optical light because optical light has a wavelength much bigger than an individual ion or atom. But because the light is coming from the source, we're able to get around this and use that loophole to look at individual ions as well. This is what loading the calcium looks like. You kind of start with a hot cloud that's still fluorescing as we cool it. And as it gets colder and colder, and also as we lower the trap potential and dump out some of the really hot ions, we're able to end up with what we call Coulomb crystals. So these crystals are essentially formed because you have really strong repulsion between individual ions, but also really strong forces in the trap. So if you get it cold enough, they'll find a long-range structure that's energy efficient, and it looks very crystalline like this. The other really nice effect is we're able to extend this to other ions as well. Because calcium is that specific energy structure, it's the only one that we'll actually directly see. However, this forces between ions that are co-sitting in the trap are very strong. Their motion's coupled. So as we cool the calcium, we cool other things sitting in the trap as well. One note on how to visualize what's happening here is these Coulomb crystals are actually ellipsoidal. They're kind of blimp shaped. But our camera focus is super narrow, so we're only actually seeing a thin slice of the whole thing. They're actually oval or cigar shaped. But when we have ions that are lighter than calcium, they collect towards the center. So we have a nice dark band so we can see that they're there. And if they're heavier, they sit on the outside like a halo. And so we can see deformation on the outside. Yes?
Right? Is it a Coulomb crystal? Or
Yes. Coulomb, like Coulomb forces. Yeah. Thank you. I tend to a little blah when I get talking too fast. So thank you. What is cool about this is we can already, with these tools, start to visualize a reaction as it's occurring. So we are exposing the ions in our trap to a gas that it will want to react with. And you can see this dark spot in the middle is slowly decreasing, and you're seeing deformation happen on the outside. And what's happening here is we're starting to react away our original ions, and some of the new product ions we're getting are heavier than the calcium, so they're sitting on the outside and squishing it in. And this is already a lot of information. However, all we know here about this reaction is that we're getting some things that are lighter and some things that are heavier. It's not very much information. So we want more tools to know what our products are. So in particular, I want you guys to discuss with your neighbor, how would you determine the mass of the ions that are in your trap? Right, go for it. All righty, where are we at? What ideas have we come up with? Yes.
Well, if we gave an additional energy and the magnetic field, we could look at the trajectory of the various ions in that field to get a rough estimate of their mass to charge ratio.
Yeah, okay, so to make sure they have some initial energy, put them in a magnetic field and then see essentially what frequency they do. So people do that. We don't, but that's a great idea, and that has been used in the field, especially in fields like you guys had mentioned, maybe using magnetic fields to track. If you already have those big magnetic fields, a lot of groups immediately go to that direction, and it's a great idea. But we don't have magnets here, and we want to look if there's a way we can do it without the magnets. Any other thoughts? So maybe in particular using some electric fields. Yeah.
Using electric fields kind of just like accelerate the particle or ions and then just measure their acceleration.
Okay, how would we measure their acceleration? You're on the right track. I love this.
Really hard.
Yeah.
Like,
Yeah, okay.
radiation.
Radiation. Okay, that's a very interesting idea. I do not think we have the tools to measure that radiation though. But if we do have two things that have different accelerations, we could also just use time, right? Could like start letting them propagate with that acceleration and then see maybe when they arrive at a target, because that's what we do. We use, maybe you've heard this phrase before, time of flight mass spectrometry. And the idea here is exactly what's been proposed, if you start with a force, so you make a large electric field, the force is the field times the charge. They have the same charge, but they'll have different acceleration because of different masses. And so if we were to say put an ion detector a good distance away and give them that initial acceleration, we can find out the differences in acceleration by seeing how long it takes them to get down to the detector. And in our trap, it looks a little bit something like this. Got an animation of the ions squeezing through this little hole, coming all the way down, almost half a meter down to a detector, right down here. And then based on the difference in the arrival times, we're able to find out the different masses that we have in our trap. And this is a very powerful tool because that then allows us, even down to individual mass units, see how the masses in our trap are changing. This is our full kind of assembly. You guys have seen most of the key parts. We have additional ways to get calcium and other ions in there, but you already know about the ion trap, the way we look at the crystals, and the time of flight mass spectrometer. And those are the really key parts. So we are ready to talk about a reaction. So this is the introduction to our reactants. These are two very interesting molecules. This is acetonitrile. So white is hydrogen, carbon, and then nitrogen. And this is a very, very chemical that it's everywhere. It's found all throughout different regions of the interstellar medium. So people have well established that this is an important one for understanding space chemistry. And it's very ubiquitous in regular chemistry as well. I could go over to the chemistry building and buy a big old bottle of it. You could even get a little bottle where there's deuteriums instead of hydrogens as well. And I have done that for this reaction. What's a little bit trickier is trying to use CCl+. So CCl+ is kind of an interesting ion because it's kind of been contested through the last several years how important it is. And it's a very difficult one to make and trap, especially because the neutral and ion are not sold in a bottle. You have to figure out how to make it, and then you got to figure out how to make it in a way that you don't have other contaminants. And this is something that our trap is able to actually do pretty well for the reasons you guys have already seen. Like I said, CCl+ has been in the past pretty hard to isolate, and that's made it pretty hard to study. But we can produce it by what we call multiphoton ionization, which is a fancy way of saying we take something even bigger and we blast it with a bunch of light, and we look at all the fragments and pick out just the ones that we want. It's a very crude way to make ions, but the great thing is that we can clean out the unwanted fragments and be left with what we want. So this is an example mass spec data. So this is the relative signal here versus mass. We have a ton of calcium because we use it for cooling. And here we have two different isotopes of chlorine. So CCl with chlorine 35 and 37. And then we have a bunch of other junk that we don't want. And we're able to clean it down to just one isotope and calcium. And that's what gets to be our starting point for the reaction. So this is pretty powerful. And that's what lets us actually take our reaction data. So this is what our reaction data actually looks like. We take that mass spec, and then we do a reaction multiple times over different amounts of time. So we always load CCl+, and then we let it get exposed to acetonitrile in the chamber for varying amounts of time. And we do it for multiple different amounts of time, and we repeat it multiple times as well. And what we're able to see when we put this data all together is a reaction. So over time, as we let more and more acetonitrile in, we lose our CCl+, and we get two new ions in our trap that are the first products. So we've assigned these to C2H3+ and HNCCl+. And then over time, they also react with acetonitrile and get an extra hydrogen. So the reaction could also be demonstrated like this. We start with mass 47. We get two different products for our first products, but they also want to react with acetonitrile. And they both end up giving an extra hydrogen to an acetonitrile. And that's where all of our ions end up. But I skipped a step. How do we know? How do we know what these are if all we have is mass spec? I'm curious if you guys have any ideas of how we could figure this out, just by raise a hand. Any ideas? Yeah.
Well, we could at least narrow the possibilities by saying we know what elements are involved and we know the relative masses. Or we know this, but that still wouldn't solve the whole problem.
Yeah, that's a great starting point because we know what the masses are and we know that we only start with these atoms, right? So there's a finite number of ways to combine those. That is incredibly powerful, actually, because when you have unlimited options, oh, there are so many molecules for all these masses. What about isotopes? This really amazing way that we're actually able to get more information than we deserve is actually what we call isotope substitution. And it's the idea that if there's two different isotopes of chlorine and two different isotopes of hydrogen and deuterium, if we substitute the isotopes in the reactants, the chemistry is usually very, very similar, but the mass is different. And we're actually able to use this to then redo the whole reaction with different combinations. And we're able to back out how many hydrogens and chlorines we have. I would never have come up with this either. This is wise people long before me, but it is a very sneaky way to be able to figure out in all of these masses how many of different atoms you have. And that's exactly what we do. There is also one other way that's really powerful, and that comes back to what I was telling you guys about the fact that these are very cold reactions. The crystals are cold. So we know that the products we have to be energetically accessible via a reaction. They can't require more energy to make than we have. And that leads into kind of the last thing I'm going to show you guys for this talk, and that's some theory results. So what I'm going to show you guys is a potential energy surface. I showed you kind of a more basic example towards the beginning of the talk. It's basically just a connection from left to right of the way that you can have bonds reform to get from reactants to products. And the way we make it is by doing what we call quantum chemical calculations, or basically energy approximations of how much energy it costs to have all these bonds and atoms sitting in this configuration. And by doing this, we can have some pretty good guesses at how much energy it takes to go through all the steps of the reaction. And this is kind of the example I showed you guys before. It's a very basic example, although real reactions are a lot more complicated. Don't worry, I'm not going to go into all the depths about this. I made this graph, I did the calculations. I've already spent too much time on it, so I won't subject you guys. But there are a couple really interesting features I want to show you. The first one is, here's our starting energy. Everything is less, which is brilliant because that means that we're able to undergo this whole reaction in an environment with no extra energy, which means it can happen in space and it can happen in our trap. One other really interesting thing it shows us is kind of the mechanism by which the chemistry takes place. And that has to do primarily with this carbon-nitrogen bond that we start with in acetonitrile. This is a really tight bond. It's a triple bond. Chemists think of this as a lot of electron density pulling these things very tightly. So it's a bond that doesn't want to break. What happens is it starts to loosen through the progress of this reaction and ultimately breaks, such that all of our products, the nitrogen and chlorine, end up together. And this is a very interesting thing because it kind of gives us a theme for how chlorine-containing reactants and nitrogen-containing reactants might tend to react with each other with this type of environment. And then the last thing we see is what our products are. We see two different ways to get C2H3+, and there's a neutral compound that would be the co-product there. And then two different ways to get HNCCl+, and then a different way to get the neutral. And this is wonderful. There we go. It is not that often that you get really great agreement between theory and experiment, but look, it's exactly what we saw in the mass spec. This is amazing. So oftentimes when we look at experiment theory together, we end up with more questions. Sometimes we just get answers. And this is a nice story where we actually just get a lot of answers, which is pretty wonderful. So in summary, I kind of wanted to show you guys how we're able to use ion trapping to look at these types of reactions at low pressures and temperatures. We're able to use theory along with this to give us an idea of how these things take place. And lastly, sometimes it takes you a while to find what you're interested in doing, and that is part of the journey. these are the people that we're able to do this with. In particular, James and Catherine worked with me on this reaction, but the group has had a lot of wonderful people throughout the time. And we are looking for more people. So if you're an undergraduate or graduate student looking to do some research and you think chemistry, physics, astrophysics is cool, come talk with me or give Heather an email. We're definitely looking for more people for our team. So thank you guys very much.
Great, thanks, Olivia. So a few announcements before we go into time of questions. So if you would like to give some feedback on this talk, we'd be happy to hear it. You can scan that QR code or go to that link that's listed up here on the slide. So next semester, our talks are going to be not at the same time. They'll be on Mondays at 5 p.m. So that may still be up for a change. So if you can't make that time, maybe you can include that in your survey if you really want to come. But yeah, if you're interested in giving a talk in the future, then feel free to reach out with that email or visit us on the website. And there are 2 events coming up as well that we want you to be aware of. So the first one, CU Prime has sponsored the class, Physics 1400. And it's basically a research-based group project sort of class, which I guess a lot of you guys here are in. And they're having a poster session coming up on December 6th. And so that is, what, 2 weeks from now? 3 weeks from now? It's sometime soon. Yes, so that'll be in this room, and there'll be refreshments, and it'll be a great time. So everybody should definitely come join us for that. And then at the beginning of next semester, in place of our first talk, we're going to have a first annual physics debate. And so we will probably be in a different room that can accommodate more people, but we'll be inviting 2 professors to come and hash out some scientific topic that there's debate on. So the theme for this next one is interpretations of quantum mechanics. More details will be coming soon. Be sure to check out the website. But yeah, just want to make you aware of what's going on with CU Prime. Okay, with that, we will go back to questions. Did we have any questions for Olivia?
Yeah.
I was just wondering, in terms of motivation, what your motivations generally are besides like availability of the reactants.
Oh, like how we choose what we do?
Yeah, like besides the availability.
Yeah. That's a great question.
Or like what's special about this reaction?
Yeah, honestly, there's a lot of serendipity involved in that. Actually, CCl plus is one we've done 2 other reactions with, and it kind of started with my lab mates trying to make something else, and they accidentally made it. And my postdoc Catherine was like, "Wow, that's actually a really interesting ion that people like have questions about. Let's work with that." And so that is actually the indirect motivation for that one. A lot of times it is, you know, oh, this is an important molecule, but sometimes it's, here's what we've got that we think will be interesting. So in other reactions we've done have actually been with calcium, because as we're doing that cooling of calcium, we're actually changing the numbers in different excited and ground states. So we can look at the reactivity as it depends on those electronic states. And so that was one that was motivated by like, we can do it, and we can do it uniquely because of how we cool our ion, so let's try it. So there is a little bit of like, oh wow, this is cool, let's just try it involved as well. Does that answer your question?
Yeah.
Cool. Yeah.
How big is the trap and how big is the ion crystal?
Excellent question. Yeah, so the trap itself is like yay big. And the actual crystal itself is about 1 millimeter by like yeah, about half a millimeter, 1/4 millimeter.
That has like 1,000 atoms in it or something.
Yeah, which is actually not that dense. When you think about, when you hear people talk about like their different atom traps, a lot of them are, especially like Bose-Einstein gases, where the whole point of them is to get super compact. Our densities are not very big because charges don't like sitting next to each other. So it's actually kind of big in the atom world, I guess, but almost big enough that you could see with your bare eyes. But I've never. My lab mate claims he sees it, but I don't believe it. Yeah. Other questions? Yeah.
There was one part where you said that there was like a subtle change voltage. Like,
Yeah.
Yeah. How fast are you changing that so that the subtle keeps like
Mhm.
the ion
Yeah, 3.5 megahertz, which is to say that it's rotating. Oh, I got to make sure I did this math right. I think it flips back and forth on the order of like a microsecond. So it's flipping back really fast. And the lighter the ions we work with, the faster it's got to go. If you think about lighter ions are moving around faster, you have to keep that trap rotating really fast to keep them. Yeah, good question. Yeah.
With the first question, we were trying to think about what actually limits the size of a molecule in space. It seems like you mentioned like the sparsity of space. There's not very much probability they knock into each other, and then also the coldness. Are there any other factors that limit like how big a molecule can get? Or what's the connection between molecule size and like reaction energy?
Yeah, great question. That's almost kind of a philosophical one, because it's kind of what the field's trying to figure out. Because you need them to be in the same place at the same time. You need it to be energetically favorable. But the other really big thing that constrains it is like how fast these reactions are. And generally, when you have little molecules, there tend to be more ways for them to rearrange in a way that's energetically favorable and really fast. But as they get bigger, those options tend to get more and more limited. But that's more of a trend than a rule. And I think part of what the field's trying to do is figure out what the rules are and which trends are really firm and which ones aren't.
Buckyball was actually single, so I wasn't finding the vision.
I'm sorry?
Was it synthesizing the lab, or was it finding the fun? Sorry. Or was it finding the vision?
The buckyball,
Yeah.
the C60, that was found in space. Yeah.
But do they use that like as in like lubrication for some of the really like precision needed?
I'm not really sure what it's been used for outside, but I do know they've definitely made it on Earth as well, because the way that they look for it is by first trapping it and measuring it in Earth experiments, because they have to figure out how it's response to light to even look for it. So anything that they found in space, they've also made here as well, which is really fascinating to think about. But I don't know too much. I know buckyball has been very fascinating for other things in nanotech, and I'm not really that knowledgeable about that.
Yeah, so you said we're able to observe and find all those type of molecules, ions in space, but do you know that these reactions actually occur at those low temperature and low pressures, or do they have like formed elsewhere and then just happens to be at those space and like, they weren't formed there? How do you know that?
Yeah, this is a big question, because there's areas of space that are really sparse, and then there's some that are kind of more these dense clouds, and there's areas where stars are being formed. And so you can imagine like there are areas of space that are a lot more active than others. But there are some constraints, because there's a limit to how far things can go in the age that we know the universe is. So there's some constraints on how far they can wander. And there's also some knowledge that we have about how fast these reactions are and how dense the population of molecules we've found are. So this kind of helps us say, okay, we can make this much, but not that much. And this much can have come from here, but not from over there. And so this is a very complicated question, though, because when you think about how big space is, how many molecules we're talking about, how many different rates and how fast to slow they go, what ends up happening is a lot of modeling to try and figure out all the different extremes that things can go. But that's a good point. Some of these things can migrate around, but there's quite a lot of them that we know have to be reacting even in these like more empty regions. Yeah.
So you mentioned obviously that you first have to start with like figuring out how these molecules interact with light. But you also mentioned that like they do radiate their own photons in response to light.
Yeah.
And when you're trying to measure that incoming light, how confident can you be that when you receive photons of that wavelength, that it's actually that molecule? It's not just light that's been redshifted or something, or maybe it's from some other source and it's a horrible coincidence.
Yes, that's a great question, and I'm pretty sure it keeps a lot of people awake at night. Thankfully, that's a little further from my job, but this is a great question because this comes into discussions about how confident you are that you've seen certain things, right? And an example of this is there are these actual, like very, very strong frequencies that they see light emitting throughout like many areas of space. And there's a lot of debate on where they've come from, because some people like they think they know it's this molecule, and other people are like, no, it's got to be these molecules. But there's some ambiguity because there's a lot of overlap. And then there's other cases as well where there's only a little bit of light, so it's harder to tell the difference between a coincidence and something meaningful. And I think the big answer is time. Over time, we get more and more data. We learn more things. Some of these kind of original measurements in the lab were from a long time ago when we didn't have as many tools. And so over time, we're able to get more and more sure of both the measurements here and in space. And that kind of helps us move slowly towards being more and more confident that we understand what we see. Does that answer your question?
Yeah.
Cool.
Thank you so much.
Sweet. Oh, keep doing that. Yeah.
How does the vacuum in your vacuum chamber compare to the vacuum space?
Great question. It really depends on what area of space we're talking about. It is not as dense as some areas, but denser than others. It's kind of in the middle. But what's actually very interesting about it is kind of this whole range of space and where our experiment lands in it is what we call the molecular regime. And it's this regime where you're incredibly unlikely to have more than two things collide at once.